Good morning, one and all. Now, in previous lecture, we have seen different usage scenarios of 5G. Now, coming to this lecture, in this lecture, we will see about minimum requirements towards IMT 2020, nothing but your fifth generation communication system. Now, all these minimum requirements towards 5G are collected from ITR recommendation 2410. From 2410 ITR recommendation, I have collected all the minimum requirements towards fifth generation system, also called as IMT 2020. Now we will see one by one what are the minimum requirements towards fifth generation system or IMT 2020, and these were collected from ITR recommendation 2410. Right. Now coming to the first requirement, here we have peak data rate. Now what is the peak data rate? It is nothing but the maximum achievable data rate under ideal conditions, and it is defined as the received data bits assuming error free condition. That means transmitter is transmitting the data and receiver is receiving the data, and these data bits are received by the receiver without any error. Assuming error free condition, it means that the receiver will receive the transmitted data bits by the transmitter assuming error free condition. That means receiver will receive the data without any error, right? Now these error free data bits are assignable to a single mobile base station only. Whatever the error free data bits that are receiving by the receiver, and these are assignable to a single mobile base station only, right? Now if we have W as the channel bandwidth and SE suffix P is nothing but a peak spectral efficiency in that particular band, then the peak data rate. Now how you will calculate peak data rate? That is denoted by RP. RP equals to W into SEP. RP is nothing but peak data rate, which is equal to multiplication of channel bandwidth and peak spectral efficiency in that band, right? Now if bandwidth is aggregated across q band, that means if bandwidth is aggregated across q bands, then the peak data rate will be R equals to summation of I equals to 1 to q. Now q indicates number of aggregated bands of the particular bandwidth. Now summation I equals to 1 to q W into SEPI. What is W? W is nothing but the channel bandwidth, and SEPI is nothing but the peak spectral efficiency, right? Now already we have discussed all these definitions in lecture 3 or lecture 4. Again I am discussing before telling the values of this particular peak data rate of fifth generation communication system, right? Now the minimum requirements for peak data rate for the downlink it is 20 gigabits per second, and for the uplink the minimum required peak data rate is 10 gigabits per second. If you find the UL to DL ratio, UL is 1 is to 2, right? 1 is to 2. If UL is 1, the DL should be 2 times of UL, right? The DL should be 2 times of UL. Now what is peak data rate? It is nothing but the maximum achievable data rate under ideal condition, and it is defined as the received data bits assuming error free condition. That means transmitter is transmitting the data and receiver is receiving the data without any error, right? The maximum achievable data rate under ideal conditions is nothing but the peak data rate. That means transmitter is transmitting the data and receiver is receiving the particular data without any error. Now these error-free data bits are assignable to a single mobile base station when all the assignable radio sources for the corresponding link detections are utilized. That means these whatever the error-free data bits that the receiver is receiving, now those are assigned to a single mobile base station only, such that all the radio sources for that corresponding link detections are utilized, right? Such that the radio sources of all of the corresponding link detections are utilized. Now the peak data rate is calculated as RP, which is nothing but the peak data rate, which is equals to channel bandwidth into peak spectral efficiency. Peak data rate is multiplication of channel bandwidth into peak spectral efficiency. Now if bandwidth is aggregated across q bands, then the calculation of peak data rate will be R equals to summation of I equals to 1 to q W, which is nothing but the channel bandwidth into peak spectral efficiency. Now the minimum requirements of peak data rate in the downlink is 20 gigabits per second, and in uplink the minimum requirement of peak data rate is 10 gigabits per second. Now DL to UL ratio is 2:1. If you consider any minimum requirement, always the DL to UL ratio is 2:1, right? Now coming to the next requirement, we have peak spectral efficiency. Next requirement we have is peak spectral efficiency. Now what is peak spectral efficiency? It is the maximum data rate under ideal condition normalized by the channel bandwidth, right? Under ideal condition, what is the maximum data rate is there, which is normalized by the channel bandwidth, that we call it as peak spectral efficiency, and its units are bits per second per hertz. It is the maximum data rate under ideal conditions normalized by the channel bandwidth is nothing but the peak spectral efficiency. Now the spectral efficiency calculations will be based on modulation, coding rate and MIMO schemes, etc. Right? Whatever the spectral efficiency that we want to calculate, now that will depend on the modulation, coding schemes, MIMO schemes that you are using in that particular technology and etc. Right? Now if you want to achieve high spectral efficiency, always spectral efficiency should be high. In order to achieve high spectral efficiency, we have to go for higher order modulation. The modulation should be higher in order to achieve the higher spectral efficiency and the maximum spatial multiplexing mode, right? You have to go for highest order modulation in order to achieve higher spectral efficiency, and also you have to go for maximum spatial multiplexing mode and the least error protection mechanism, right? Now the things should be received without any error. That mechanism has to be used in order to achieve high spectral efficiency. Now the minimum requirements for the peak spectral efficiency in the downlink. In the downlink is 30 bits per second per hertz, and in the uplink is 15 bits per second per hertz. Now if you see this DL to UL ratio, downlink to uplink ratio, again it is 2:1. If you consider any minimum requirement, in previous also we have seen DL to L ratio is 2:1. Now in this particular peak spectral efficiency minimum requirement also, the ratio of DL to UL is 2:1. Now the antenna configuration that is required is up to 8 spatial layers, nothing but 8 streams in the downlinks and 4 streams in the uplink. The antenna configuration that we can go up to 8 streams in the downlink and 4 streams in the uplink, right? Now what is the peak spectral efficiency? It is nothing but the maximum data rate. Peak spectral efficiency is nothing but the maximum data rate which is normalized by the channel bandwidth under ideal condition. Maximum data rate, whatever the maximum data rate is there, which is normalized by the channel bandwidth under ideal condition, that we call it as peak spectral efficiency. Peak spectral efficiency is nothing but the maximum data rate under ideal condition normalized by the channel bandwidth. Now its units are bits per second per hertz, right? Bits per second per hertz are the units of peak spectral efficiency, right? Now the peak spectral efficiency calculation will be based on modulation, coding schemes, coding rate and the MIMO schemes, etc. Right? Whatever the peak spectral efficiency that we want to calculate, that will depend on the modulation what we are using and the coding rate and the MIMO types of MIMO schemes what we are using in that particular generation system and everything. All these are responsible for the calculation of spectral efficiency. Now in order to achieve high spectral efficiency, we have to go for higher order modulation. If you go for higher order modulation, obviously the peak spectral efficiency increases, right? And also one more technique you have to improve is you have to go for maximum spatial multiplexing. In order to achieve high spectral efficiency, you have to go for higher order modulation and maximum spatial multiplexing and least error protection mechanism. These are the three techniques through which you can improve the or you can achieve the higher spectral efficiency. One is you have to go for higher order modulation in order to improve the spectral efficiency. Now you have to go for maximum spatial multiplexing in order to achieve higher spectral efficiency, and another one is least error protection mechanism. These three are responsible for achieving the higher spectral efficiency, right? Now coming to the minimum requirements. Now the minimum requirements of peak spectral efficiency in downlink. In downlink is 30 bits per second per hertz, and in uplink the minimum requirement of peak spectral efficiency in the uplink is 15 bits per second per hertz. Now if you see this DL to L ratio, it is again 2:1. The previous one is also DL to L ratio is 2:1. Now here also 2:1. Now the antenna configuration support will be 8 streams in the uplink, 8 streams in the downlink, and 4 streams in the uplink. Again, if you see the antenna configuration, the DL to L ratio is also 2:1. You have 8 streams and in the downlink and 4 streams in the uplink. The DL to L ratio under antenna configuration is also 2:1, right? Now always you have to remember the requirements in the downlink will be more if you compare with the requirements under the uplink. In the coming requirements also you will see DL to L ratio will be 2:1, right? Now coming to the next requirement, we have user experienced data rate. What is the user experienced data rate? We have already seen this term under lecture 3. We have seen different terminologies under lecture 3 or lecture 4. Again I am discussing this. Now it user experience data rate. It is nothing but the 5% of the cumulative distribution function of the user throughput during active time. If you see this figure, you will have a clear idea. Now the cumulative distribution function is on y-axis and user throughput on x-axis, right? Now the CDF value will vary from 0 to 1 and the user throughput values will vary on the x-axis, right? Now the 5% of the user throughput of the cumulative distribution function is nothing but the user experienced data rate, right? This particular, if you see this particular box, now this is the 5% of user, this is the 5% of user throughput, right? Now this 5% of the cumulative distribution function of the user throughput is nothing but the user experienced data rate. Now what is the active time? Active time is nothing but the correctly received bits, which is equals to the number of bits, right? Whatever the number of bits that are present in the service data units, that should be equals to the number of correctly received bits which are delivered to the layer 3 over certain period of time, right? With delivering to a particular layer over certain period of time is nothing but the active time, right? Now what is user experience data rate? It is nothing but the 5% of the cumulative distribution function of the user throughput. If you see this figure, you will have a clear idea. Now the cumulative distribution function is on a y-axis, which will vary from 0 to 1. On x-axis we are having user throughput. Now this is the particular graph. Let us assume now this 5% of the user throughput of the cumulative distribution function, 5% of the cumulative distribution function of the user throughput, we call it as user experienced data rate. What is user throughput? This 5% of the cumulative distribution function of the user throughput is nothing but the user experienced data rate during active time, right? Now what is active time? The number of bits that are present in the service data unit should be equals to the number of correctly received bits, and these bits are delivered to a layer 3 over certain period of time, that we call it as active time. Whatever the data bits are that are present in the service data units that are transferred to the layer 3 over certain period of time, and this should be equals to the number of received bits, that we call it as active time, right? Now what is user experience data rate? It is nothing but the 5% of the cumulative distribution function of the user throughput during active time. What is active time? It is nothing but the number of bits that are present in the service data units which are transferred to the layer 3 over certain period of time, right? Now the number of bits that are present in this SDU should be equals to the number of received bits, right? Now if you see this figure, you will have a clear idea. Now this is the cumulative distribution function of the user throughput. Now this particular S shape, this is nothing but the cumulative distribution function of the user throughput. Now this 5% of the cumulative distribution of the user throughput, we call it as user experienced data rate, right? Now here we have two cases, right? In this particular user experience data rate, we have two cases in order to calculate user experience data rate. One is one frequency band. Coming to case one frequency band and one layer transmission. One layer means like CISO transmission only. CISO transmission reception point, in bracket we have represented it as TRXP, transmission reception points, right? Now the user experienced data rate could be derived from the 5th percentile of user spectral efficiency, nothing but the 5th percent of the CDF cumulative distribution function of the user throughput, right? What is a user experience data rate? It is nothing but the 5% of the cumulative distribution function of the user throughput, and the value we calculate by using this formula, that is R user, right? R user experience data rate of a, which is equals to W. What is W? Bandwidth into spectral efficiency of that particular user, spectral efficiency of that particular user. R equals to W into SE is nothing but the calculation of the user experienced data rate, right? Now next case, here we have it as multiple frequency band. Now case 1, we have one frequency band and one layer transmission. Now here we have multiple frequency band. Using this formula, we will calculate individually. For one band we will calculate one user experience data rate, and for next band we calculate another value. Now adding those all those values will give you the multiple frequency band. For multiple layers, the user experience data will be summed over the band. Individually, we will calculate using this formula, that is R user equals to W into SE user. Now, upon calculation of individual values and later adding all those values will give you the multiple frequency bands user experienced data rate, right? Now, the target values, nothing but the minimum requirements of downlink user experience data rate is 100 megabits per second, right? Now 100 megabits per second is the minimum requirement of user experience data rate in downlink, and for uplink we have 50 megabits per second, right? For uplink we have 50 megabits per second, and for downlink we have 100 megabits per second. These are the minimum requirements of user experienced data rate, right? Minimum requirements of the user experienced data rate under downlink and up. Now here also, if you see DL to L ratio, again it is 2:1, right? Again it is 2:1. Always you have to remember one point: the downlink will be having the highest value if you compare with the uplink, right? Now what is user experience data rate? It is nothing but the 5% of the cumulative distribution function of the user throughput, right? Now here we calculate in two different ways. User experience data is calculated in two different ways. One is case 1, under which one frequency band and one layer transmission. If you have only one frequency band and one layer transmission, like example CISO, now the calculation of the user experience data rate is given as channel bandwidth into spectral efficiency. Channel bandwidth into spectral efficiency. Multiplication of channel bandwidth into spectral efficiency will give you the user experience data. Now if you have multiple frequency band, we will calculate individually and later we will add all those values for the If you have two bands, like let us assume if you have two bands, more than one band, right? If you have two bands, for R1 we calculate W into SE, and for R2 we will calculate W into SE, and later we will add R1 plus R2, right? R1 is nothing but user experience data rate for one particular frequency band, and R2 is nothing but user experience data rate for second frequency band. We will calculate individually and at last we will add those values in order to get the user experience data rate under multiple frequency band. Here I have represented for multiple layers, the user experience data rate will be summed over the bands. Individually we will calculate user experience data rate for each particular band. For each particular band we will calculate user experience data rate. At last we will add all those values, right, in order to get the user experience data rate under multiple frequency band. Now the user experience data rate, the minimum requirement of user experience data rate in downlink is 100 megabits per second, and in uplink the minimum requirement of user experience data rate is 50 megabits per second. This is one more requirement, user experience data rate, which is nothing but the 5% of the cumulative distribution function of the user throughput, and here we will calculate using the formula R user equals to W into SE user. If you have one frequency band, directly you can calculate using this formula. Now if you have multiple frequency band, we will calculate individually for each frequency band, and at last we will add all those values in order to get the user experience data rate under multiple frequency band. Now the target value of user experience data rate in downlink is 100 megabits per second, whereas in uplink it is 50 megabits per second. Now again here DL to UL ratio is 2:1. Now coming to the next requirement, we have normalized throughput. Already we have seen this under lecture 3 or lecture 4. Again I am saying just a definition, right? Before entering into the values, we will have the definition of each individual term, so that you will have a clear idea about that particular term, right? Now the normalized throughput is given by gamma I, which is equals to xi by ti dot w. Now what a xi denotes? It denotes the number of correctly received bits by user I, right? It is the ratio of number of correctly received bits of user I to the ti denotes active session. Ti denotes active session, where w is the channel bandwidth, right? Normalized throughput, right? Normalized throughput is nothing but it is the ratio of number of correctly received bits of user I to the active session time into channel bandwidth, right? Now the normalized user throughput of user I is given by gamma I, which is equals to xi by ti dot w, where xi denotes the number of correctly received bits by user I, and ti denotes the active session time for user I, and w is the channel bandwidth, right? Now if there are only now let us take an example. Now let us assume you have only 10 correctly received bits by the user. That means for user I we have received only 10 correctly bits. Now what xi will denote? Xi is nothing but 10 correctly bits. Now during the active session of some 5 milliseconds or 5 microseconds, you will assume, and the channel bandwidth is 60 kilohertz. Let us assume. Now how you will calculate normalized user throughput? That is given by xi. What is xi? Number of correctly received bits. Now how many bits we have? We have 10 bits. 10 divided by ti is nothing but the active session. Now what is active session? Active session is nothing but number of correctly received bits should be equals to the number of correctly transmitted bits, and those are transmitted during some time ta. Those are transmitted during some time. That particular time we call it as ta. Now that time we have taken as some 5 microseconds or 5 milliseconds into channel bandwidth, that is given by 50 kilohertz we have. Now the calculation of that value will give you the normalized throughput, right? Now what's the value? Bits per second per hertz. Now units are bits per second per hertz. Here you have under numerator you have bits divided by, and ti units are seconds, and channel bandwidth is in terms of hertz. Bits per second hertz, right? Now this is the normalized user throughput. It is given by xi divided by ti into w, where xi denotes the number of correctly received bits of user I, and ti denotes the active session time for user I, and w is the channel bandwidth. Normalized user throughput is given by xi divided by ti into w, number of correctly received bits by active session time into channel bandwidth. What is active session? The number of transmitted bits should be equals to the number of received bits, such that these bits are transmitted at a during a particular time of time. That particular time we call it as TL, right? Now the channel bandwidth you know already, right? Now coming to the next, we have, now this table indicates the minimum requirements of fifth percentile user spectral efficiency for various test environments, like indoor, dense urban, rural. These are the three different test environments for which the minimum requirements of fifth percentile user spectral efficiency in the downlink as well as in the uplink. Those are represented in this particular table, right? Now coming to the test environment indoor hotspot, EMBB, nothing but enhanced mobile broadband scenario in the indoor hotspot. Now the downlink bits per second and units are bits per second per hertz, and downlink here we have minimum requirement of fifth percentile user spectral efficiency is 0.3, and in uplink here we have 0.5. 0.21. If you see this, always the downlink value will be greater than the uplink. Now under dense urban test environment, now the downlink fifth percentile user spectral efficiency value is 0.225, and in uplink here we have 0.15, and whereas in rural we have 0.12 in downlink and 0.05 in uplink, right? Now this particular table, if you see this particular table, here we have represented three different test environments. One is indoor and dense urban and rural, right? Indoor is nothing but within the building, and dense urban is nothing but where there are large number of people, and rural you already know it, right? These are the three test environments, right? Now, and the minimum requirements of fifth percentile of user spectral efficiency in this particular test environments, that is indoor, hotspot, dense urban, rural. These the for the in this test environments, the minimum requirements of fifth percentile user spectral efficiency in the downlink as well as in the uplink are represented in this table, right? For the indoor hotspot, the minimum requirement of fifth percentile user spectral efficiency in downlink is 0.3 bits per second per hertz, whereas in uplink it is 0.21 bits per second per hertz, right? Now in test environment of dense urban, in dense urban test environment, now the minimum requirement of fifth percentile user spectral efficiency in downlink is 0.225 bits per second per hertz, and in uplink it is 0.15 bits per second per hertz. Now coming to the next test environment, here we have rural. Under rural test environment, the minimum requirement of fifth percentile user spectral efficiency in the downlink is 0.12 bits per second per hertz, whereas in uplink it is 0.05 bits per second per hertz. If you see these values, always the downlink values will be greater than. If you take any requirement, any term, always, that means any terminology, if you take, whether it is user experience data rate or whether it is peak data rate or whether it is area traffic, if you consider any terminology, always the downlink values will be greater than the uplink values, right? Now this particular table, uh, in this particular table we have represented three different test environments, and the minimum requirements of fifth percentile user spectral efficiency in the downlink and in the uplink we have represented in this particular table, right? And coming to the next we have next requirement, we have average spectral efficiency. Average spectral efficiency, right? Now the average spectral efficiency is given by summation I equals to 1 to n xi divided by t into w into m, right? Now the average spectral efficiency that is given by summation I equals to 1 to n xi divided by t dot w dot m, that is multiplication of t with w with m. Now what xi denotes, as we already know, xi is nothing but number of correctly received bits by user I in the downlink or in the uplink, right? In the downlink or in the uplink in a system consisting of n users. Now let us assume if a system has n users, right? If a system has n users, now xi denotes number of correctly received bits by a particular user. I includes in that particular n users, either it may be in the uplink or it may be in the downlink, right? Now what is t? The time over which the data bits are received, right? Now already w, you know, channel bandwidth. Now m denotes the number of transmission and receiving points, right? TRXP is transmission and receiving points, right? Now this is the formula to calculate average spectral efficiency, which is given by summation I equals to 1 to n xi divided by t dot w dot n, right? Now for n users, if a system consisting of n users, xi denotes the number of correctly received bits by user I, either it may be in the downlink or it may be in the uplink. Now t indicates number of data bits which are received over a particular time. That particular time we call it as t. T is nothing but the time over which the data bits are received. Now w is the channel bandwidth and m denotes the number of transmitting and receiving points, right? Now this is the formula to calculate average spectral efficiency, which is also called as spectrum efficiency, that is given by summation I equals to 1 to n xi divided by t dot w dot n, that is multiplication of t with w with m. Now if a system has n users, right, xi denotes the number of correctly received bits by user I, either it may be in the downlink or it may be in the uplink. Now t is nothing but the time over which the data bits are received, w is nothing but channel bandwidth, and m is nothing but transmission and receiving points, right. Now we will see these values, the minimum requirements of average spectral efficiency in three different environments, right. Now the minimum requirements of average spectral efficiency in three different environments, test environments, as we have seen in previous slide also: indoor, dense, urban, rural, right. The average spectral efficiency will be in downlink, it is 9 bits per second per hertz per transmission or receiving point, right. The units are bits per second per hertz per transmission or receiving point, because we have summation I equals to 1 to n xi divided by t dot w dot m. M denotes the number of transmitting and receiving points, right. Now in downlink it should be 9, average spectral efficiency should be 9, and in uplink it should be 6.75. Again, if you see this, downlink value is greater than uplink. Now under next test environment, here we have dense urban test environment. Now for this environment, the average spectral efficiency is 7.8 bits per second per hertz per transmitting and receiving points in downlink, and 5.4 in uplink. Now coming to the next test environment, here we have rural. Under rural test environment, under downlink, we require average spectral efficiency of 3.3 bits per second per hertz per transmitting on receiving point, and in uplink its value is 1.6, right. Now in this particular table we have represented three different test environments uh, for which we require the average spectral efficiency in downlink and uplink, right. We have represented three different test environments, those are indoor hotspot, dense urban, rural, right. For this particular three test environments, we have represented the values, the minimum requirements of average spectral efficiency for downlink as well as uplink. Now coming to the test environment indoor, the average spectral efficiency in the downlink is 9 bits per second per hertz per transmitting and receiving point. For uplink it is 6.75. Now under dense urban test environment, the average spectral efficiency requirement is 7.8, and for uplink it is 5.4. Now for rural test environment, the average spectral efficiency is 3.3 in downlink and 1.6 in uplink, right. Now these are the minimum requirements of average spectral efficiency in the downlink and the uplink in three different environments, that is indoor, dense area and rural, right. Now coming to the next requirement, we have area traffic capacity, right. Now the next requirement towards 5G we have is area traffic capacity, right. Now it is described as the total traffic throughput served per geographic area in megabits per second per meter square, right. What it means is that in a particular geographic area, the total traffic throughput, serving of the total traffic throughput, we call it as area traffic capacity. That means within a particular area, whatever the total traffic throughput is there, that we call it as area traffic capacity, and its units are megabits per second per meter square, and it is given by area traffic capacity, which is denoted by C area, which is equals to rho into W into SE average. What is rho? Rho denotes the transmitting receiving density, right. Transmitting and receiving points density. TRXP is nothing but transmission and receiving points, and rho denotes its density. W denotes, you already know, channel bandwidth, right. SE average is nothing but the average spectral efficiency, and again that is given by summation I equals to 1 to n uh, xi divided by t into w into m. Already we have seen in previous slide. Now the area traffic capacity is calculated by C area equals to rho into w into SE average. What is rho? It denotes the density of transmitting and receiving point, and W is the channel bandwidth, and SE average is nothing but the average spectral efficiency, and the formula we have represented in the previous slide. Now the target value of area traffic capacity in downlink is 10 megabits per second per meter square, right? 10 mbs per square meter or meter square, and in the indoor hotspot, right? In the test environment of indoor hotspot, this is the particular value that we require in the downlink for the area traffic capacity. Now coming to the latency, you already know latency. Now here we have two different latencies. One is user plane latency and control plane latency. Now the minimum requirements for user plane latency for EMBB. What is EMBB? Enhanced mobile broadband. The user plane latency requirement is 4 milliseconds. Now whereas for URLLC, ultra reliable low latency communication, URLLC, which is nothing but ultra reliable low latency communication, for this scenario we have three different usage scenarios, right? In previous lecture we have seen we have three different usage scenarios of 5G. For different usage scenarios of 5G are broadly classified into three different usage scenarios. One is enhanced mobile broadband, and next we have URLLC, ultra reliable low latency communication, and another one is massive machine type communication, right? For EMBB we require user plane latency of 4 milliseconds, and for URLLC we require user plane latency of 1 millisecond. Again I am discussing what is area traffic capacity in a particular geographic area. In a particular geographic area, the total traffic throughput, whatever the total traffic throughput that is serving in a particular geographic area, that we call it as area traffic capacity, right? The total traffic throughput serving in a particular geographic area, the total traffic throughput serving in a particular geographic area, we call it as area traffic capacity. What is area traffic capacity? It is nothing but the total traffic throughput serving in a particular geographic area, right? Now its units are megabits per second per meter square. Now it is calculated by formula area traffic capacity, which is equals to rho into W into SE average. What is rho? It denotes the density of transmitting and receiving points, and W is the channel bandwidth, and SE average, you already know, average spectral efficiency, right? Average spectral efficiency. Now the minimum requirement of area traffic capacity in the downlink is 10 Mbps per meter square, and in the test environment of indoor, right? In the test environment for dense urban it will vary, and again for rural also it will vary. For indoor only I am saying, for the indoor hotspot, the minimum requirement of area traffic capacity in the downlink is 10 Mbps. 10 Mbps, P is not represented here, but it should be 10 Mbps, 10 megabits per second per meter square. And again in uplink you will have a value which is less than the 10 Mbps per meter square. Now coming to the latency, here we have two different latencies. One is user plane latency and control plane latency. And again, what are the we have different usage scenarios of 5G, and those are broadly classified into three different scenarios. One is enhanced mobile broadband, which is represented as EMBB, and we have URLLC, which is nothing but ultra reliable low latency communication, and next we have massive machine type communication, right? Now the minimum requirements of user plane latency for EMBB is 4 milliseconds, and for URLLC is 1 millisecond, right? Now coming to the next requirement, we have control plane latency, right? Latency is broadly classified into two types. We have seen what terms control plane latency and user plane latency under lecture 3 or lecture 4. You can refer that, right? Now user plane latency is for EMBB it is 4 millisecond, and for URLLC it is 1 millisecond. For EMBB user plane latency is 4 millisecond, and for URLLC ultra reliable low latency communication it is 1 millisecond. Now coming to the another plane latency, that is control plane latency. Control plane latency refers to the transition time from idle state to the active state. The time taken in order to the time taken in order to go from idle state to active state, right? Whatever the time that is taken by a system or the thing from the idle state to active state, that particular time we call it as control plane latency. And the minimum requirement of control plane latency is 20 milliseconds, right? Now the minimum requirement of control plane latency is 20 milliseconds. Now coming to the another requirement, here we have connection density, right? Connection density, number of connecting devices per kilometer square. Connection density should be high for your fifth generation communication system. Now it is the total number of devices. Connection density is nothing but the total number of devices fulfilling QoS. QoS is nothing but quality of service. Quality of service per unit area. Total number of devices fulfilling quality of service per unit area is nothing but the connection density. Now the QoS is to support delivery of a message of a certain size within a certain time and within a certain success probability. That means quality of service means you have to deliver a message of a particular size within a particular time, and you have to deliver the message with maximum of success probability. Now the minimum requirements for the connection density. Now the minimum requirements for the connection density is, here we have 10 power 6 devices per kilometer square. We have 10 power 6 devices per kilometer square is the requirement of connection density in the fifth generation system. Now coming to the another requirement, here we have energy efficiency, right? The energy efficiency, we have the energy consumption should be decreased. If you go from one generation to another generation, 1G to 2G, 2G through 2G to 3G, 3G to 4G, 4G to 5G, the consumption of energy should be decreased because it will play a vital role, right? Now if you go from 5G to 6G also, again the energy consumption should be decreased, right? Now the energy efficiency, when user is not using any data, the energy consumption should be low, right? And the efficient data transmission in a loaded case, right? Now these are the two things that are to be supported by the fifth generation system, right? Now coming to the latency, we have two different latencies. One is user plane latency and control plane latency. Now the minimum requirements of user plane latency for EMBB, enhanced mobile broadband, is 4 milliseconds, whereas for ultra reliable low latency communication is 1 millisecond. Now coming to the another plane latency, that is control plane latency. Control plane latency is nothing but the transition time from idle state to active state. Control plane latency refers to the transition time from idle state to active state. Now the minimum requirement of control plane latency is 20 millisecond, right? The minimum requirement of control plane latency is 20 milliseconds. That means 20 milliseconds is the minimum requirement in order to transit from idle state to active state. Now coming to the next requirement, we have connection devices. It is nothing but the number of connected devices fulfilling quality of service per unit area per kilometer square. It is nothing but the number of devices fulfilling quality of service per unit area. Now what is meant by quality of service? It is nothing but the delivering a particular message of particular size within a particular time, and that should be delivered with a success probability. Now the minimum requirements of connection density is 10 power 6 devices per kilometer square. That means within a area of kilometer square, there should be 10 power 6 devices should be connected to the fifth gen under the connection. That means 10 power 6 devices should be connected within an area of kilometer square under 5G. Now coming to this, as you go from one generation to other generation, the energy consumption should be decreased, right? Now that can be decreased by two techniques. One is efficient data transmission in a loaded case, and low energy consumption when there is no data, right? Now coming to the next requirements, we have reliability. You know what is meant by reliability. Now this ultra reliable low latency communication test scenario, which we have represented in yesterday's lecture, that is URLLC, ultra reliable low latency communication scenario, in which we have very high success probability and during low latency, right? Reliability you already know, that means latency is low. Using URLLC scenario of 5G, we have broadly classified into three different scenarios. One is enhanced mobile broadband, ultra reliable low latency communication, and another one is machine type, massive machine type communication. Now among these three different scenarios, this ultra reliable low latency communication test scenario, uh, in which we can expect very high success probability under low latency, right? Under low latency, we expect very high success probability. Now coming to the next requirement, we have mobility, right? You know what is meant by mobility. Now stationary indicates 0 km per hour under ideal condition. That means the person or the thing is not moving anyway. That means 0 km per hour. Pedestrian just a walking, that is 0 to 10 km per hour. Vehicular, you already know, that is 10 to 120. It is not 129. It is 10 to 120. 10 to 120 km per hour. Now high speed vehicular is nothing but 120 to 500 km per hour. 120 to 500 km per hour. Already you know this uh, classes, but again I am representing here mobility. Now this mobility values under different test scenarios, I have represented here. Now we have three different test scenarios. One is indoor, dense urban, and rural, right? Now for the indoor, the normalized traffic channel link data rate, will be 1.5 bits per second per hertz. This is the minimum requirement of normalized traffic channel link data rate under indoor test environment, that is 1.5 bits per second per hertz, and the mobility will be just a 10 km per hour, that is under the state of pedestrian, and that will be under the state of pedestrian. Now coming to the dense urban, here we have the normalized channel link data rate is 1.12 bits per second per hertz under the test environment of dense urban, and the mobility will be 30 km per hour. That means it will come under the state of vehicular, right? Now coming to the rural test environment, now the normalized traffic channel link data rate is 0.8 bits per second. Now the mobility will be 120. That is high speed vehicular, right? Now again under rural only we have one more class, that is 0.45 bits per second, which is of normalized traffic channel link data rate, and the mobility will be 500. For different mobilities, the normalized traffic channel link data rate will be varied, right? Now what is reliability? We have URLLC scenario through which you can expect high success probability under low latency communication, under low latency condition. Now you know mobility, we have four different classes. One is stationary, which is of 0 km per hour, pedestrian class, which is whose value is varying from 0 to 10 km per hour, and vehicular mobility class, that is 10 to 120 km per hour, and high speed vehicular mobility class, that is 120 to 500 km per hour. Now this particular four mobility categories, we have represented normalized traffic channel link data rate, right, with three different test environments. In this particular table, we have represented under three different test environment what are the values of normalized channel link data rate and what is the mobility in that particular test environment, that we have represented in this particular table. Under the test environment of indoor hotspot, the mobility will be 10 km per hour, and the traffic channel link data rate requirement will be 1.5 bits per second per hertz, right? Under dense urban test environment, the mobility will be 30 km per hour, and the traffic channel link data rate will be, the minimum requirement of traffic channel link data rate will be 1.12 bits per second per hertz. Now coming to the under rural, if the mobility is 120, the traffic channel link data rate requirement will be 0.8. If the mobility is 500, the traffic channel link data rate will be 0.45, right? Now these are collected from the ITR recommendation. These are the minimum requirements towards the IMT 2020, nothing but your fifth generation system. We have seen different requirements. One is user experience data rate, peak spectral efficiency we have seen, and next we have seen different mobilities under a different test environments, average spectral efficiency. All these are the minimum requirements towards the IMT 2020 or the fifth generation system, and all these requirements are the values that we are collected from the ITR recommendation, right? And in the next class we will see the basic signal model, right? We will, and the next class we will see the now the theory part ends here, and in from the next onwards we will see the signal models. After that we will see the waveforms under 2G, waveforms under 3G, and waveforms under 4G, and later we will go for waveforms under 5G, right? Till now we have seen the IMT requirements towards um, fifth generation system, that is nothing but IMT 2020, and all these are collected from the ITR recommendation. In the next lecture we will go for the basic signal model, right? Thank you.